Good afternoon. My name is George Dimitrakopoulos, and I will present our work with my colleague Grigoris Kostopoulos and Professor Stelios Georgantzinos. The title of this work is Tolerance Analysis and Assembly Performance Enhancement in 3D Printed Mechanical Components. A review. This is a literature review on tolerances in additively manufactured components and their effects, where assembly performance combined with the proposed generic workflow dedicated to AM assemblies. In this slide, I briefly present the structure of the talk. I will start with the motivation and scope, very briefly revisit the basics of tolerancing and GT&T, and then discuss AM specific challenges. After that, I will move to experimental finding on deviation, benchmark, artifact, datum systems, and the influence of process parameters. I will then present the predictive models, tolerance-cost relationships, and studies that focus on assemblies. Finally, I will show the proposed workflow and then main assumptions. This is a research review combined with the proposed methodology. Additive manufacturing enables complex and customized mechanical parts, but dimensional and geometrical deviations are available. The literature shows that these deviations propagate to assemblies and can lead to misfits and reduced reliability. There is therefore a need for systematic tolerance analysis frameworks tailored to AM parts and assemblies. The goal of this work is to review and classify the relevant methods and based on the identified gaps to propose a generic workflow for rapid tolerance analysis and improve assembly performance. In essence, this is a review paper with a proposed process. In this slide, I briefly recall the fundamentals. There are classical tolerance analysis methods such as worst case statistical analysis and Monte Carlo simulations, which have been extended to three-dimensional tolerance analysis for assemblies. GD&T is a standard language used to express functional requirements such as flatness, position, and run-out following ASME or ISO. The key message is that the tool exists, but they were developed mainly for conversations, processes, and need to be adapted on the specific characteristics of AM. I present the AM specific challenges. The layer-wise build process causes stair-stepping, anisotropic syngates and warp aids. Supports and scan strategies introduce additional systematic deviation and surface defects. Many studies report non-Gaussian and operational dependent error distribution. The common finding is that many classical tolerancing assumptions do not fully hold for AM, so tolerance models need to be redesigned to reflect process-specific behavior. In this slide, I summarize the experimental finding on dimensional and geometrical deviation. Many studies measure linear dimension and geometrical tolerances such as flatness, cylindricity, parallelism, and position. Overall, the deviation shows size-dependent bias, significant scatter, and a strong dependence on the orientation and process parameters. The table and the plot indicate that typical tolerance capability for AM lies between IT9 and IT16, which can be used as a realistic baseline when designing fits for 3D printing parts. I discuss benchmark artifacts and related standards. I saw that NIST AM test artifact and the polymer metal tolerance artifact that are used to assess geometric capability and derive ISO IT grades for different AM technologies. I also refer to reviews on artifact design and the ISO ESN-PRESS, which standardizes test geometries and measurement procedures. The key message is that without standardized artifacts, we cannot reliably compare tolerance data from different machines and laboratories. I will focus on datum systems. The same AM components can be evaluated with different datums and different hierarchies, and this can significantly change the measurement results. The work by Grigoris and co-authors, for example, shows that the datum choice affects the calculated tolerance and the compliance with specifications. The conclusion is that for complex and free-form AM parts, we need AM-aware datuming strategies so that measurements have a different functional meaning for assemblies. Here I link process parameters to accuracy. The literature shows that layer thickness, build orientation, laser power, and scan speed have a strong effect on dimensional and geometrical accuracy. In addition, pre-processing workflow and data preparation play a role. Taguchi and Doi studies for FDM show that only a few parameters, such as layer height, print speed, and the nozzle diameter, explain most of the variability. The main effects plot clearly identifies the critical settings. These results can be used as input distribution in Monte Carlo simulation and capability analysis. Here I discuss predictive models and machine learning. The figure shows a typical pipeline where measurement data and feature from design and process feed an ML model that predicts local geometrical deviations. The literature indicates that such models can offer better predictive performance than simple linear models. What matters for us is what these models can be used as inputs to tolerance analysis and conversation strategies for AM parts. Now I remind the tolerance-cost relation. The classical tolerance cost curve also applies to AM. As tolerances are tightened, cost increases due to longer build time, higher scrap rates, and more post-processing. Work such as Roth's and the review by Holman show how tolerance cost models can be developed specifically for fused layer modeling. For the designer, this means that tolerance selection is also an economic decision. A balance must be found between functional requirements and acceptable cost. DFMA strategies propose parts consolidation, adjusted clearance, and choosing nominal dimension according to proposed bias in order to improve an assembly's robustness to deviation. At the same time, the number of studies that explicitly investigate assemblability indices locating error of or robustness is relatively small and often based on specific demonstration assemblies. The figure shows an example on AM-oriented design where the assembly becomes easier and less sensitive to dimensional variation. This is the central slide of the proposed workflow. We start by designing representative test components and assemblies. They are manufactured by AM under control process windows, and the critical dimensions and geometrical tolerance are measured. Based on this data, we build statically deviation models and process capability models. These models feed to tolerance analysis, which is directly linked to assembly performance metric such an aligned back class and preload. Finally, the results are used to optimize design and process parameters and are validated on functional assemblies. And finally, in this slide, I conclude the presentation. The literature provides extensive data on dimensional and geometrical accuracy for individual AM parts, but there are fewer studies that consider complete assemblies and integrated workflow from process parameters and assembly performance. There is a need for unified AM specific tolerance standards and for better integration for statistical and ML models into practice. The proposed workflow can serve as a basic for future experimental and industrial work. Thank you for your attention, and I will be happy to take any questions.